from beautiful Fairbanks, Alaska. My name is Peter Griffith. I'm the Director of NASA's Carbon Cycle and Ecosystems Office at Goddard Space Flight Center, and I'm very excited to be the project manager for NASA's Arctic Boreal Vulnerability Experiment. And we are here in Fairbanks with NASA's DC-8, an aircraft that is at the moment getting prepared for flight. We're going to be flying from here in Fairbanks to Southwest Alaska, testing out a suite of very exciting new remote sensing instruments. And these fit into above this Arctic Boreal Vulnerability Experiment in a really essential way. Our desire with above is to understand the consequences both to ecosystems and to society of rapid environmental change in the Arctic and Boreal region of the world. Now, when I say Arctic, lots of people always think of vast expanses of ice and frozen things, and that of course is true. But this project is looking at the part of the Arctic that is wet and green and covered with animals in the summertime. And that's what we've been flying over this year in order to better understand the consequences to the whole world of the rapid changes that are occurring in this area. Now, we are looking at changes in the Great Northern Forest, changes in forest fire frequency. We're looking at changes in permafrost. These are the soils of the region that are permanently frozen and that are now thawing and releasing carbon dioxide and methane into the air. This particular aircraft is especially equipped to better understand what is happening on the ground and how it's influencing the Earth's atmosphere. And you'll find out a little more about that when I introduce you to one of my colleagues in just a minute. So let's step inside this, kind of think of this as this is a 1969 vintage aircraft. It's sort of like a long, thin Cadillac. It is built like a truck, and that's exactly what it is for us. It is a truck that carries instruments and scientists into the air to study the Earth's environment. So let's go inside. It looks a little bit different than some of the commercial aircraft that you're accustomed to being in. It might get a little busy. We're prepping to close the doors in about 20 minutes, and then we're going to start flying. We've got 8 crew and 16 scientists on board. And as you can see, there's we have a mission manager table here. Gentlemen, how are you? And I'd like to take this moment to introduce you to my colleague, Dr. Chip Miller from the lab. Hi, Chip. How are you?
Hey, good morning, Peter. How are you today? All right.
So, Chip, I've just told them a little bit about the Arctic Boreal Vulnerability Experiment, or above, and some of the big questions that we're looking at in this northern region. But maybe you could give folks an idea of the scope of the airborne remote sensing that is being used during above.
Certainly, Peter. So, above has one of the largest airborne campaigns that's ever been mounted by NASA's Earth Science Division. We have a total of 17 different deployments of 9 aircraft and sensor suites stretched from April through October of 2017, and this will amount to more than 200 individual science flights. One of the reasons for this very large-scale undertaking is that the area that we're trying to sample is nearly 4 million square kilometers, which is about 2 million square miles, and ranges from Arctic tundra through the boreal forest. And we're going from as far west as the Seward Peninsula all the way in the east to Hudson's Bay western shore, and from the Arctic Ocean coast in the north to the southern edge of the boreal forest, which is near the U.S.-Canadian border. Okay?
Thank you, Chip.
No worries. All right, moving on.
Okay. Now I'd like to introduce you to Jim Abshire, Dr. Jim Abshire from Goddard Space Flight Center. And he is the mission scientist for this deployment of this aircraft, and he's going to tell you about some of the instruments on board and what some of the observations and the science questions are that this particular flight is going to be addressing.
Okay, well, yeah, thank you, Peter. So yeah, we have an important part of the Above campaign. We're funded actually by Above and also Ascends. The NASA Ascends program is working toward launching a CO2 measuring satellite to allow us to make accurate measurements of CO2 globally, and also in the Arctic and in the darkness, which present satellites can't do. So we're measuring CO2 very accurately on this aircraft with several different techniques. We have 3 different in situ measurements that bring in air into the aircraft and put them through analyzing equipment. We have, again, 3 of them in racks here, there, and here. And then we also have 2 LiDARs, and the LiDARs measure CO2 in the column from the aircraft altitude down to the surface.
Tell them what a LiDAR is.
A LiDAR is just like a radar, but we use laser beams instead of radio beams to measure. And both these measure CO2 absorption in a particular absorption line. The more absorption we have, the more CO2 there is in the column. So there's 2 of these toward the back of the aircraft. They're slightly different, so we're testing how well they work. Those measurements will be valuable not only to Above to look at the column CO2 in the Above study area, but also help us better understand how to develop the Ascend satellite.
So in NASA in general, we use a lot of our airborne remote sensing to develop the instruments that ultimately we launch into space. And so that's very specifically what this aircraft and the instruments on it are involved in. It's developing spaceflight hardware.
Yeah. So this campaign is really nice in the sense that we get to not only look at that, but also the science we're contributing will be a big benefit to the Above investigations, and particularly in sampling the atmospheric CO2.
Thanks, Jim. You want to show us the panel back here?
So we have numerous instruments. Again, we have 3 in situ instruments that we just passed, and we have the LiDAR instruments toward the back of the plane.
Gentlemen, how are you?
Hey. So this is one of the 2 LiDARs. This is the ACES LiDAR. So inside here are lasers and that send light through the bottom of the aircraft. There's a window, and we receive backscatter from the surface and from clouds in a telescope, and that's detected inside this box as well. And then the data is recorded back here in a rack of computers. And here are our ACES investigators. And we also have this is from NASA Langley. We also have the NASA Goddard instrument that works. In principle, it's spread out across 3 different racks here. Here's the transmitter assembly and the receiver telescope assembly. It works in a very similar fashion, but with somewhat a different LiDAR measurement technique.
So, Jim, we've got a couple of good questions here.
Okay.
So the first one is, what about the fumes the plane will release? Will you be taking that into account?
Well, that's a very good question. The fumes, our in situ sensors measure the air before the engines, so they don't affect the measurements. And the LiDARs measure straight down, so the plumes actually go behind us, so they don't impact our measurements at all.
Yeah, thank you.
Okay.
And then we have, what are some of the challenges you expect in this experiment? We can take that specifically for your activity, and then maybe Chip or I will say something about the challenges.
The challenges scientifically, the CO2 impact the fluxes, the emission and absorption of CO2 by the surface produce only very small perturbations in the total column. So we're looking for very small changes in the CO2 column with these instruments. And the big challenge with respect to airborne measurements and also for the Ascends mission in the future is measuring these changes less than 1%, measuring them with enough accuracy to allow us to understand the processes, the fluxes that are coming from the surface.
Yeah. I'll say as a project manager that one of the big challenges of this project, we have over 60 investigations. most of those are funded by NASA, but we have very important partnerships with Polar Knowledge Canada and the Canadian Forest Service, Department of Energy, NOAA, and working across the scientific coordination for that many different projects has been very challenging. We also have several hundred people deployed in the field that are making the essential ground observations that are important for all of the remote sensing that's being done. And that includes with the CO2 measurements. There are instrument installations called flux towers that are actually mounted in frameworks on the ground and are measuring the CO2 and methane that is coming from the surface and entering the atmosphere. And of course that, as Jim was saying, that's also a challenge because when the more sunlight there is, the faster the plants are growing, there's more CO2 being taken up. And at night in places where it gets dark, it doesn't get dark quite yet here, the respiration of the plants and animals are releasing CO2 and sometimes methane into the air. So these ground sites are very important.
Hi, we're back. Okay, so following on to what Peter said, from the perspective of planning and then implementing the science investigations, it's extremely challenging to make the measurements where and when we would like to make them because of such things as cloud interference, prohibiting some high-quality data acquisitions of our remote sensing imagery. We want to have the planes flying over at the same time as we have teams on the ground in the field making their measurements so we can coordinate those things. And getting all of this to work smoothly is quite a challenge, particularly with the changing weather and the relatively poor weather forecasting for this part of the world. So that's been another thing that we've overcome.
I have another great question here. When will the results be published? That's a very important question. All of the data that NASA takes from on the ground, from aircraft, and from satellite assets in orbit are provided to everyone in the world. They're all published in an open form where anyone can access the raw observations that we take. And with something as complicated as this, and with research grade instruments where people are still figuring out how to calibrate and validate all of the data, it may take up to a year from the original observation before the data are released to everyone in the world. Now, the publications in scientific So we're back online? All right, so I was talking about NASA's Arctic Boreal Vulnerability Experiment and the availability of data and of publications. We already have papers that are available that are coming out from work that the precursor work that inspired this large-scale experiment, and even some of the work that was just funded in the past year or two are starting to come out in paper form. We have a website, above.nasa.gov, where you can find a lot of that kind of information.
While Peter's looking at the next question, I looked at the Above website just the other day for this exact reason, and there are more than 70 papers that the Above science team have already published, and publishing continues at a rather rapid pace, so I would expect that number of papers will grow tremendously over the next year or three.
So we have another good question. Why use the DC-8? Why not use hundreds of data measuring drones? That might, in some cases, that could be the end result after a long period of development.
Yeah.
But if we look again at this instrument that Jim was just showing the folks, this is a little large for a drone. And Jim, if you want to add anything more to that.
No, that's exactly right. The DC-8 is very well suited for instruments, for larger instruments in this stage of their evolution. They're large, they take a lot of power. We almost always need operators to do the adjustments as they're being developed. Once they're developed, if there are large drones, NASA has Global Hawks, for example. It's possible they could be flown on that after more engineering is done. But again, you need to ensure that the instrument performance you can build an instrument that would fit into a drone, and that's not possible with LiDAR right now.
One other thing that NASA is investigating at the moment is the switchover in the satellite realm from a few very large satellites to using this idea of a swarm or constellation of many smaller satellites with smaller instruments to make similar measurements.
I'm not seeing any new questions right at the moment. How's our time looking? We're good?
Well, I was just going to follow on your publication question. We have the American Geophysical Union conference coming up this December. I'm sure there will be a huge group of papers presented. They're not quite published, but they'll be presented to the public and to the attendees on the results of the above campaign and also the Ascends campaign flights.
That's right. We do have, thanks
Yes.
for bringing that up, we do have a special session at the American Geophysical Union in December in New Orleans. Another question, why launch a CO2 satellite? Why not invest the same amount of money in expanding the ground-based observation?
Okay. Well, if the world was covered with habitated places, you could do this with ground-based observations. But there's many areas of the world, 70% is ocean. The Arctic and the Antarctic areas are very sparsely populated. So you need really a satellite to get the global coverage to answer the important carbon cycle questions.
So I was the deputy principal investigator of the original Orbiting Carbon Observatory satellite project, where we investigated why you would make these measurements from space. And very simply, we're bringing back more than 1 million measurements around the world every day from different places with the current OCO2 satellite. And this is something that we just cannot do with a ground-based network. We don't have 1 million sensors. We have of order about 100 sensors around the world. So even though they're measuring continuously, it's this spatial distribution of information that is the key asset that the satellites bring back.
And there's simply no way you can expand this network of 100 to get the global coverage that you would need that a satellite can provide.
Correct.
And the satellites also measure the total amount of CO2 in the entire atmospheric column from the surface to space.
Yeah.
So
now, to be fair, each of these is part of a total integrated tiered observing system where we use aircraft and ground-based measurements and measurements from space to put together a picture that we would not be able to get using any one of these different kinds of measurement techniques.
yes, that's all part of the scaling strategy from leaf to orbit, as our dear colleague Piers Sellers used to like to say, of having the observations on the ground from the towers, which gives a little bit larger spatial scale, from aircraft with even broader spatial scale across this region, and then ultimately viewing from space. Here's a good one, Chip. Do we know how much CO2 and methane is trapped in permafrost and tundra in the Arctic?
What a great question. We covered that a little bit yesterday in the Snapchat session that we had, which people might still be able to find online. This is something that's called the permafrost carbon feedback. There are literally billions of tons of carbon trapped in the frozen soils and permafrost of the northern high latitudes. And the permafrost carbon feedback is trying to figure out what happens when permafrost thaws and this carbon that had previously been trapped becomes released. Our modeling and our understanding of the science of this is relatively uncertain, so we don't know with high confidence how much of this carbon will be released, where it will be released, when it will be released, and what molecular form, whether it's carbon dioxide, methane, or dissolved organic carbon that gets carried off by the rivers into the oceans. We don't know much about any of these things. So this is one of the reasons that we're bringing all of these assets to bear to study the northern high latitudes, to understand better this permafrost carbon feedback, which many think may be as large as the fossil fuel combustion inputs that we've had since the beginning of the Industrial Revolution.
Thank you, Chip.
No worries.
Hey guys.
Yes.
Time to go.
Time to wrap?
Yeah, we have to go do the mission now.
Okay.
I know.
Thank you.
Strangely, we actually have to go fly to get all this stuff.
This is actually...
You guys want to introduce yourselves?
I'm Nate.
Nice to meet everybody. We're going to have a great flight today. It's an absolute beautiful day in Alaska, and it's going to be an excellent flight. We're going to get a lot of science, and maybe we'll start this up again tomorrow.
Yes.
Well, gentlemen, thank you for keeping us on task.
Yeah, thank you. Thank you.
Let's do it, guys.
Thanks. That's my job, right?
Thank you, everybody who's been watching in.
Thanks, everyone.
Thank you. Thank you. Thank you for watching.